Hello, I'm Anirudh. I'll be presenting a work to derive robust planning strategies from cognitively biased models of environment. This work was carried out at Rationality Enhancement Group at Max Planck Institute for Intelligent Systems. So let's begin with the motivation behind our work. We want to develop algorithms which help us discover good planning strategies and teach them to people. Sometimes true environment underlying rewards might not be available to us, hence we would need to train algorithms based on models obtained from people's description of environment. But their perception of environment might be cognitively biased, hence algorithms trained on it might not discover strategies that would work well on the real world. In this project, we intend to solve this using Bayesian inference and provide a first proof of concept to solve such problems. Let's look at the overview of our work. At first, we build likelihood models of common cognitive biases. We receive possibly biased environment models from people. Given this biased environment and our model of cognitive biases, we use Bayesian inference to get a posterior of true environments. The obtained environments are those true environments which under some cognitive bias might have been perceived by people as biased environment. Now we train algorithms using all these possible true environments so that they can discover strategies that would work good on any of the true environments. At last, we use a tutor to teach the discovered strategies to people who use these strategies on the true environment to improve their decision making. As planning and strategies are difficult to infer directly, we use a process tracing paradigm. Here, we need to move the plane from the bottommost row to one of the nodes in the topmost row. Each node contains an underlying positive or a negative reward, and user collects the reward underlying the nodes as he moves. Further, there is an option to inspect the node and find out the underlying reward at a cost of $1. Hence, the objective is to collect the maximum reward as he moves up, at the same time minimize the number of clicks. If the rewards were distributed at random, then there wouldn't be any particular strategy on which nodes to inspect. But what if the underlying rewards are distributed in a pattern? Suppose there are three kinds of node: high variance H, medium variance M, low variance L, whose rewards are sampled from the values shown here. So if the pattern of underlying rewards are as shown here, then we see that the maximum information about the nodes are available with the high variance nodes. We would want to collect the high positive rewards and at the same time avoid the high negative rewards. Hence, inspecting leftmost column only and taking our chances on the other two columns might be a good strategy. We must note that if the pattern of underlying rewards change, then the optimal strategy would change as well. Link to the process tracing paradigm has been provided in the poster. Coming to the modeling of cognitive biases, we here assume that people's description of environment may be distorted by recency bias or the underestimation bias. In the recency bias, people may misremember the first two steps as being similar like the third step. Hence, in the structure, we see that the bottom two rows being mistaken to be similar to the top row. The underestimation bias might cause people to forget array reward distribution and misremember it as the most frequent one. Here, we see the top row being mistaken similar to the bottom two rows. Hence, we see that the strategy learned on the biased environment might not work on the true environment. Bayesian approach to robustness. First, we find out the posterior distribution over the possible true environments given the biased environment and the likelihood model of the common cognitive biases. Then we train algorithms on samples from the posterior. Three algorithms were considered: deep recurrent Q learning, deep meta-reinforcement learning, and Bayesian meta-level policy search. Coming to the simulation results, with Bayesian inference indicates that the algorithms were trained on samples from the posterior. Without Bayesian inference indicates that the algorithms were trained only on the biased environment. We find that the Bayesian inference improves the performance on all the three algorithms. BMPS with Bayesian inference performs the best. Comparison of strategies learned by robust method versus the non-robust method. Both the algorithms were given same biased environment. In the top row, we consider the true environment to be the same as the biased environment. We find that both algorithms discover similar strategies. But in the bottom row, we consider the case when the true environment is not equal to the biased environment. We find that the non-robust tutor clicks same nodes as earlier, which is not a good strategy when applied on the true environment. But we see that the robust algorithm adapts itself, clicks the nodes that are optimal for the true environment, and hence performs better. As we want to teach these discovered strategies to people, we did an experiment on Amazon Mechanical Turk with 300 participants. Three conditions were considered. In the robust tutor condition, people were shown demonstrations of click sequences from BMPs with Bayesian inference. In the non-robust tutor condition, people were shown demonstrations of click sequences from DRQN without Bayesian inference. In the control condition, there were no demonstrations shown. The experiment was modeled as follows. There were 5 practice trials for the people to get used to the environment, then 10 demonstrations of strategy discovered by the algorithm was shown, followed by 15 test trials. We see that people trained with robust tutor perform significantly better than the other two conditions. To conclude, we find that Bayesian inference and considering people's models of cognitive biases helps us discover better strategies. These discovered strategies can be taught to people to improve their decision-making capabilities. Future work would involve applying these methods to more complex and real-world scenarios and developing other methods of teaching people these discovered strategies. Thank you for listening. We would love to hear from you.